Salut, dați-mi vă rog un semn dacă sunteți online și mă auziți. Bun, perfect. Mai stăm 2 minute că nu-mi dau seama cât suntem conectați. Mi-arată aici că suntem 0, dar evident suntem mai mulți. 24, e bine. Ok, haideți să începem cu o recapitulare și după aceea să intrăm în materialul nou. Notițele de curs încă nu sunt aduse la zi, trebuie să introduc acolo toate exemplele astea cu explicații, explicații care le-ați... Oh, sorry guys, I have to speak in English. All right, switching to English now. So, I'll start with a review of what we've done last week. And before that, I just want to mention that the lecture notes are not up to date. I have to include there all these examples that you see and the explanations that you've heard or will hear today. Yeah, sorry about that. I taught the Romanian class and I kind of got stuck on Romanian, but here we go. However, while the lecture notes are not up to date, all these examples that I'm working on can be found on the class website. If you go here to examples done in class, lecture and thread examples, this is it, all right? So this is what I'm teaching. And you'll get the rest of it with explanations and all that sometimes this week. Another announcement where can I turn the, maybe I'm speaking low, is this better? 1, 2, 3, 1, 2, 3, can you guys hear me? I don't know how to turn the microphone up. It seems to be maximum. All right. Just a bit better. All right. I'll try to use my voice like one of those opera singers. Okay. So you've seen where the examples are. I also want to remind you that next week we will have tests, the first round of tests. You will take the grep, sed, and awk test along with the shell test. Your lab professors should have or will this week do some kind of a rehearsal with you to see how the connection to the exam server is done, how things will be done, and then next week you'll get you'll get the first round of exam. Then the next week next week is the first round of tests. Next week the shell exam. 1 week nothing, and then C threads and processes test, and then threads and processes exam, and then we're kind of done. So this is if you want a look ahead. Now let's have a review of what we've done last week. We started threads, and we started comparing threads with processes, and we saw that while a process copies its parent process image, clones it, and then continues from where it was left, thus duplicating quite a bit of memory. Threads don't do that. Threads reuse the process's memory and only get a piece of it to use for stack. Also, processes have not having any memory in common need some special mechanisms to communicate, whereas threads have the global variables, the heap, available to them so that they can communicate through those, just like processes could do using shared memory. The problem is that shared memory without any synchronization gives strange results. So we ended up needing synchronization, right? We also talked about how to pass arguments to threads. And we've seen a wrong example, which is quite appealing because it's very simple. You just send the address of a variable, but if you end up sending the same to all threads, weird things will happen. So you can see this in param wrong, and then I gave you a number of examples of how to pass parameters to threads, ending in this dirty one, which is quite comfortable, but not that great an idea. I am using it, however, to reduce the clutter in the examples. And then we reached the part where threads need to aggregate results. And that means practically modifying some kind of variable common to them all. And we saw how this can lead to problems. For instance, this was the example that we looked at. 21. And then this is how we fixed it. Right, so we created 10 threads, all running function f, then we waited for them, and then all these 10 threads performed n++ about 1 million, actually exactly 1 million times. And running this, we noticed that the results were really wrong. So we figured out that n++ is not atomic, and consequently it gets sort of interleaved, and then the end result is not what we expect. So then we fixed this by adding a mutex, and the mutex was the first synchronization mechanism that we talked about. Mutex comes from mutual exclusion, meaning that it provides a function called lock, which only one thread can go through at a time. So we defined the mutex, we initialized it. You can look at this one to one because they're the same, just this one has empty lines where this one adds the mutex code. So we initialize the mutex, and then we destroy the mutex at the end. And then in the function, we surround n++ with a lock unlock, which means that out of these 10 threads, whichever manages to pass through the lock, right, which means get the lock on the mutex, that thread will do n++. The other threads will simply wait to get the lock while this guy does the n++. When this guy is done, unlocks the mutex, another thread will get the lock and do n++. So with this, what we did is synchronize access to the so-called critical resource. So in these situations, the variable that is modified and read simultaneously by many threads, it's called a critical resource because access to it causes problems, right? So this is critical. And then the section of code touching that variable is called the critical section. Then the critical section is this. So the critical resource is n, critical section is n++. So we always protect the critical section with some synchronization mechanism, in this case, a mutex. Okay? And after this point, we looked at a special case for which we came up with a mechanism that was a little something like an optimization. And I'm talking here about the read-write lock. So the special case, which one? Okay, fine. The special case is when the critical resource is read many, many times, but it's written much less. And an example is people looking to buy tickets. Lots of people look at what's available and only a few actually buy. And in this case, you need to somehow synchronize the access to, let's say, that variable that holds the number of seats available. You need to synchronize it. You need to synchronize it for the people who buy, but you also need to synchronize it for the people who check, because you want them to see a consistent image of what's available, not see something that is actively modified at the same time, and thus see, let's say, half new information and half old. So now if you want to synchronize a situation like this, you could use a mutex. and the functioning will be correct, but it will not be performant. Why? Because although the mutex solves the race condition, you will have every single reader read by itself. And you don't need that. You need to ensure that only one thread changes things at a time, and you can have any number of threads reading at the same time, but you want to make sure they don't mix. So you either have any number of threads reading or only one writing, no mixing. Okay? And in this situation where writers are not too many, but reads are lots, you bring in the so-called read-write lock, which is similar to mutex, but it has two types of locking methods. One of them is, wait a minute, this is the wrong one. This is the wrong example here. I think I need 33. No, 36, 39 even. No, I guess this one. Yeah. So you get a read-write lock, and then you have the two locking methods. You have a write lock, which is used for the threads that modify, and you have a read lock, which is used for the threads that just look at the value. So a read lock, many threads can pass through the read lock as long as there is nobody holding a write lock. And only one thread can get a write lock as long as nobody else holds either a write lock or a read lock. So this kind of optimizes things, allowing many readers to look at the data at the same time, and also making sure that whenever somebody changes it, nobody else either reads or writes. So this is the read-write lock. And then this is where we stopped last time. And now we are going to look at the next synchronization mechanism, which is called a conditional variable. And a conditional variable, it's actually, the name is not necessarily intuitive. It doesn't quite reflect what it does in the basic case. But I will start with that and then move to the full use case, which will actually clarify why it's called a conditional variable. So in the simplest way of using a conditional variable, and this is the usage, right? The operation goes like this. A thread waits until another thread wakes it up. Okay, so the conditional variable actually does some kind of wait until notified. And you will find this same functionality in Java and probably other languages, but I don't know how they name it. And it's just called wait and notify. So how does this work? I have a thread waiting on the conditional variable, and I have another thread signaling the conditional variable, which in turn will wake up the waiting thread. So let's look at the code. I declare a conditional variable and a mutex. This is another important point. You can never use a conditional variable without a mutex. They have to be in conjunction. They have to be together. So we initialize both mutex and conditional variable. At the end, we destroy both. And then we just create two threads, one with function fa and one with function fb, and then we wait for them to finish. So these two threads, what they do is the following. fb waits. Now, for now, just ignore the lock unlock here. I will get to it. But basically, what fb does, it is to wait on the conditional variable. And what fa does, 10 times prints out something and signals the conditional variable so that fb wakes up. Right? That's all that it does. So if we are to run this, and I have it compiled already, so I'm now going to compile it again. The execution looks like this, and I'm going to execute it a number of times until I get something different, like this. So what do we see here? FA goes on and and cycles 10 times and signals the conditional variable 10 times. And in the end, B wakes up, right? Just wakes up from here and prints. But this is not always the same. Sometimes FA cycles only 8 times and then B wakes up. So this is consistent with the undeterministic way of thread execution. You don't know who gets the processor and when. So what is happening actually is that signaling is not really anonymous with shaking the other thread to wake up. It's mostly like setting a flag in the conditional variable structure saying you have to wake up somebody. And then is the system's job when it intervenes and interrupts FA to check and see, oh, the conditional variable has been signaled. Let's see who's waiting and wake them up. Which means that between the signaling moment and the wake up moment, there will be a time that will pass. And in that time, other things happen. For instance, you see FA signals in the first moment, but then it keeps doing it because it keeps getting the processor, and FB doesn't. So A gets the processor and just cycles 10 times. It just signals 10 times. Eventually, B gets the processor and prints out. Okay, so we have Headshot Spy asking, what if we call FB first? So there are two things to answer here. First of all, you're not calling FB. You're creating a thread with FB. And if you do that, the notion of first doesn't really do much, doesn't really mean much. You created the thread. After this point, you have the main thread and the thread running FA. After this point, you have three threads. You have no idea which one of them will get the processor. Hence, you have no idea who will be first. It may just be that this finishes before this even starts. You don't know. Okay? But what happens is this guy gets in, sits waiting on the conditional variable, and then at a point, the system interrupts this guy and notices that it signaled the conditional variable and then gives processor to this guy. And then this guy goes and prints out. But this doesn't happen at any certain moment. It just depends on how the operating system chooses to schedule things. So now, well, this is really easy. You wait until I signal you. There is also the matter of mutex to discuss. And also, I want to mention that there is also a function called broadcast. Signal will only wake up one thread waiting at the conditional variable. You can have many waiting for it. So signal wakes up one, broadcast wakes up all. Okay? So now what's with the mutex? The need for the mutex will become evident in the next example where we do the full usage of the conditional variable. But suffice to say that you cannot really do this, either signal or wait, without having a mutex lock unlock around it. So just take this as I'm giving it to you. You lock the mutex, you signal, you unlock. You lock the mutex, you wait, you unlock. And then here, you may have a question. You may be looking here and say something like, wait a minute. You're just locking the mutex, and then you're going into wait. I mean, you hold the mutex and then you do nothing. How is this guy supposed to lock the mutex since you're holding it and sleeping? How can that happen? And the answer is indeed, I lock the mutex here and then I'm going to waiting. And if that's all I did, then nothing else would move because I would sleep with the mutex locked and nobody else could do anything. However, you may notice that I am passing the mutex to the wait. And wait, actually, the first thing that it does, it is to unlock the mutex. basically making sure that the mutex is available for other operations, and then it goes into waiting. When it wakes up, it doesn't return until it catches again the mutex. So as a colleague of yours said it, FB actually touches the mutex 4 times, 2 times explicitly that we wrote the code, and then in here you have also an unlock and then followed by a lock. All right. So when you go into wait, the mutex is released. That's when this guy can spin and do his work because it can get the mutex. But when this guy wakes up, it will lock back the mutex, right? Leaving practically, when you come back from wait, you will still have the mutex just like you did before. And this will go to also tell you that it's natural to have a distance between signal and actual wake up, because once you signaled, this guy needs to get the processor in order to wake up. So there will be a duration of time between signaling and FB getting the processor. But even after it gets the processor, there will be a battle for the mutex, because this guy has to lock the mutex back again, and it will battle for that lock with this guy. And you don't know who will win. Maybe this guy wins. So then this guy will stay here until it gets the mutex. Consequently, it will take some time to wake up before the signal. Okay, so we have here another question. What does change? So what does change the conditional variable and when? I'm not sure what you're asking. What do you mean, what does change? What does change? Who changes the conditional variable? I'm not sure how to answer this. A thread signals it or broadcasts to it, another waits for it. There is, what other change would you expect? Please rephrase the question and I'll try to answer. So this is it. This is the basic usage. One signals, one waits. Now let's see the full example. And this example will make clear that the conditional variable will work in conjunction with an actual condition, ensuring that the wake up will actually act only if the condition is satisfied. Okay, conditional variable is not like a bool. No, yeah, you're right. I never thought of this, but you could think of it. If it's called conditional variable, it might be a boolean. No way. It's actually a structure for which you wait, and another thread can wake you up. Now you'll see where the condition comes in. So let's open the next example, 42. Now this is gonna be a beekeeping example mixed with bear feeding example. So we'll have 3 threads. One will be actually not 3 types of threads. We will have bear threads, we will have bee threads, and we will have one farmer thread. Okay. So the idea is this. The whole program starts with a certain amount of honey. Bears will eat honey 1 unit at a time. Bees will produce honey 1 unit at a time. But if the honey goes to 0, then the bears wake up the farmer to bring some more honey from the deposit because they are hungry. So the farmer wants to keep the bears happy. The bees produce honey, but maybe not in the necessary rhythm. And when there is no more honey, the bears should wake up the farmer to produce more honey. Not to produce, but to provide. So let's see the main function, what it does. This is actually quite simple. We will have 21 threads. This clock time thing is only so that the program runs for 5 seconds. So I'm just measuring, and after 5 seconds we stop. So we initialize the mutex, we initialize the conditional variable, and we create the farmer thread. And then we create 10 bees and 10 bears. Okay? Then we wait for all threads to finish, destroy the mutex, destroy the conditional variable. So main is actually quite simple. The B threads do this. While go will become false after 5 seconds. So for 5 seconds it keeps cycling and it does what? Lock the mutex, increment honey, unlock the mutex. So that's what bees do. So we'll have 10 bees that will keep producing honey. The bears, hold on, because I think I can fit the whole thing on the screen. The bears eat honey. They lock the mutex, right? For 5 seconds, they lock the mutex. If there is honey, then they eat. If there is no more honey, they signal the conditional variable, and this will wake up the farmer. And we print out an exclamation mark so that we know that the bear was in distress and woke up the farmer, right? I mean, signaled the farmer. And then the bear unlocks and then spins again, locks. If there is honey, eats. If not, signals the farmer. In the end, after 5 seconds, the bear signals the farmer just to be sure that it wakes up, because it may be that the farmer was never signaled, and then the farmer would keep sleeping even after the 5 seconds. So these 3 lines are put there just to make sure the farmer doesn't get stuck. Okay, so let's see some questions. Do you need to have the same number of bees and bears? No. Why would I need? I can make as many as I want. But in this case, having them equal number makes the example varied enough so that you see the necessary behaviors. If I have too many bees, the farmer will never wake up, right? If I have too many bears, you're not going to see how the farmer wakes up and goes back to sleep without doing anything about the honey. So that's why I chose equal numbers, because I will get these behaviors visible. This is a very unsustainable ecosystem. I agree, William, if this would be an actual system, but it's not. It's all fake. There is no bear. It's only written. Honey is gone. Funny. Okay, now let's see what the farmer does, because this is where things get interesting. What the farmer waits to be notified. But you remember that there will be a time delay between the farmer being signaled and the farmer actually kicking into action. And it is possible that in this interval, the bees get to produce honey. So it may be that the bear says, oh, there is no honey, farmer, wake up. But by the time the farmer wakes up, the bees catch up with the honey and there is no shortage anymore. In which case, the farmer shouldn't do anything. But if when the farmer wakes up, the honey is indeed zero, then it should do something. So this is how the farmer looks like. It also cycles for 5 seconds, locks the mutex. And here is the difference. Before we just said wait, but now we check the condition. As long as we still have to go, right, we're not beyond the 5 seconds, and the honey is greater than zero, then just, well, sleep. Wait to be notified. Okay? But this is a while, so I would like you to wonder why it's a while. If I wake up, I check the condition again. If I'm still within the 5 seconds and there is no more honey, I'll jump out of the while. I'm not going to be waiting anymore. I'm going to say okay and add 100 units of honey. Okay? But if when I wake up there is enough honey, I just go back straight to waiting. So let's run this example and see how it works. So let's read this. farmer sleeps. The bees don't say anything. The bees just produce honey. They don't print out anything. But the farmer goes to sleep, right? Waiting to be woken up. And the bear comes in, and one bear and says, well, there is no more honey. It wakes up the farmer, and it just happens that the farmer gets the processor and says, okay, and adds honey. And then it goes back to sleeping. But then the bears again notify it, this time 2 times before it wakes up. And watch this. The farmer wakes up, but it doesn't go to the okay. It just goes right back to waiting. Because between the moment it was notified and the moment it actually woke up, the bees produced enough honey so that when it looped again through the while, honey was greater than 0 and it went back to sleeping. And this happens here and here and here, and then finally here, it wakes up at the moment when the honey is negative, I mean 0, and it produces honey and then goes back to waiting. And then here is a lot of notifications. Eventually the farmer wakes up and says, okay, and produces honey. So I would like you to look at this code now and come up with questions. I'll leave this on the screen. And I want questions because this is not exactly intuitive. It's usually difficult for students to understand it, but with a little effort, it's not going to be much to work on. But if the farmer locks the mutex before going to sleep, how is it modified by the bears and bees? How is it? What's modified? Thank you, Berzent. I think that's what William is asking. Wait will release the mutex before actually waiting, because otherwise, indeed, bees will not be able to lock here, nor bears will be able to lock here. The answer is in the wait. The wait releases the mutex. So please wonder why this is a while and not an if. And or if it's not clear, ask. But what you see here, this is the standard way of using a conditional variable. So let me open here. I have a little Scratch file. Oh, this is something else. So if you have the bear and the farmer, I can write the logic a little more concise, skipping the mutexes. The bear will say signal, and the farmer does a while honey greater to 0, wait. Okay, so the bear signals, the farmer wakes up at a point, but it cycles back and rechecks the condition. It doesn't just go into action. If the code was written as the following, so if the code looked like this, then the farmer would only check at the beginning whether it should wait or not, the first time it goes in. And then as soon as he's woken up, it will jump and add more honey, which will create a surplus of honey because sometimes when it wakes up, there is no need for honey. It's been filled in by the bees in the meanwhile. So if doesn't really solve this issue, if only makes sure at the beginning, should I wait or not? While is the one that solves the problem because after you wake up, you recheck the condition. And if the condition is still okay, you go back to waiting. If it's not, then you jump out of the while and then you go here and you produce honey. All right? It's also important to notice that Because wait locks back the mutex before coming back, this condition is evaluated under, actually this is the one that matters, after, this is evaluated under the protection of the mutex. So I will wait for your questions here. Right, we have a long question. So the farmer is constantly idling. Yes, is a constantly idling listener thread. Isn't that wasting processing power? What about making the farmer react when the honey goes under zero? But that's what it does. That's exactly what it does. Uh, this is not spinning. The, the farmer actually does nothing here. This is not a while honey greater than zero, check again. This is it. While honey is greater than zero, wait to be told it's below zero. So this is actually implemented reacting. The farmer reacts to this signal. It's just that by the time it gets to react, the condition may have changed, and then it just goes back to waiting. All right, I don't know the analysis what to do with that. Okay, William clarifies. What I mean is, can we make the farmer do something else at the same time? Do something else at the same time. Not with this API. I think I know where you're going. You're thinking event-based programming. But what I'm showing you here is right under event-based programming. This is underneath the hood. So event-based is a little above this. So no, this will not do anything else. We'll just wait. If you want something else to happen, create a thread and have that do something else. All right, let's see. We have Costim saying, so while if just for the eventual case when the bees make honey, so he can go back. So the while is, yes, Costim, that's right. What the hell are you guys doing with all these faces here? Isn't the go in the second while redundant? Thank you, Alex, for this question. Isn't the go in the second while redundant? All right, you have to stop with these small comments, because I can't answer the questions. No, it's not really, because if you wake up the farmer and the honey ends up being greater than zero, but you're beyond the time, right? You're at second 7, let's say, it will go back to waiting. So you have to make sure, because otherwise it will stay stuck forever. So this is not really redundant. What else do I have? So can signal is like waking up. What's the name? Philalita07. It's not like waking up a thread. It's like putting a notice on the conditional variable. So the way this works is this. Threads don't really wake up by themselves. It's the operating system that does it. You have a bunch of threads available, and then the operating system kicks in at every so often, interrupts the execution of the current thread, and then looks at the available threads. And with an algorithm called scheduler, chooses who goes next. So the bear doesn't really wake up the farmer. The bear only marks the conditional variable as signaled. Now the scheduler, when it looks at the available threads, notices, oh, the farmer has been waiting on a conditional variable that is now signaled. So let's wake him up. All right, so it's not like the bear wakes it up, but the bear, in a way, tells the operating system to wake it up. And when that happens, we don't know. It may be after a while. Okay. Then we have here a lot of drop, which I don't know what it is. While is, yeah, I got it, that Costin. Is there going to be a giveaway later for subs? What the heck is that? I'm not really sure how to answer that. Oh, you're just making fun. That's fine, guys, but I'm I'm not really up to date with all these jokes, so I don't know how to answer, but I I'll make an effort. Not today though. Okay, William asks, we need the wild because if we have multiple farmers, they would all add honey instead of only the first one, unless we check the honey. I agree with this, William, but even if you have a single farmer, you may still end up in that situation. Look, here the farmer eventually woke up, but it didn't go to okay. It went right back to sleep because there were no other farmers to bring honey from the deposit, but there were bees who in all this time produced honey. Okay, Stefan. So this scheduler, yes, the scheduler is always up and kicks in every so many microseconds and choose a next thread to run. Berzent. So it's more like the bears go on strike and tell the government to make the farmer give them more honey. But then they get the honey, so the government notifies the farmer when they have time. Yeah. The farmer wakes up and the bears are no more on strike. Exactly. That's perfect. So then the farmer goes back to sleep because the problem solved itself. Right? And we don't want the farmer to do anything if the problem is not actually active anymore. So this is why they call it a conditional variable, because it's used in conjunction with a condition, which also shows up here. And this condition is also protected by the mutex that the conditional variable gets. So it's all interlinked. All right, now we have AOS, DNA, ASO. Oh God, your names. Regarding the while loop in the farmer thread, it is checking whether there is still need of honey after the wait. But what if we use the code with if and put another if after the wait? Okay. What you're doing with your suggestion is check twice, but not every time. So what AOS DNA SO, actually I can read that, AOS DNA SO. So what you're suggesting is this. Right? This is what you're suggesting. So this will work fine if we only wake up the farmer once. But if we wake the farmer 2 times, it will not work anymore, right? So it checks the honey, honey is plenty, it goes to wait. It wakes up. If the honey is still okay, it goes to wait. If it again gets woken up, then regardless of how the honey is, it goes and adds. Whereas this guy works for every single wake up. I'm waiting for other questions if you have on this. And we have Irelia, and how could we make this code 100% reliable? I mean, to make the farmer reliable wake up every time the bear. All right, so what you're looking for is not really reliable. What you're looking for is to add honey every single time it reaches 0, and then you just have to work either sequentially or come up with a way of stopping the bears from doing anything until the farmer kicks in and adds honey. But this is not what the conditional variable are made for. They are not really made to wake up exactly when you say. They actually model the real world. Somebody says, go do that. It will take a while for you to do that. And in the meanwhile, there will be things happening. If you want the effect of your signal to be immediate, that actually means that you will not do anything until the farmer, you as a bear will not do anything until the farmer adds honey. And then it's your job, after you wake up the farmer, to wait for the farmer to add honey. So maybe you'll be waiting on a conditional variable and the farmer notifies you back. That would be a way. So in a way, what Irelia is saying, can we give turns to each other? As a bear, I keep eating. When there is no more honey, I will stop. And it's the farmer's turn to produce honey. And after he produced honey, he stops, and it's my turn to eat. So this is like a game, it's my turn, it's your turn, it's my turn, it's your turn. You can solve this with mutexes, but you need to build more than just this. Okay, let me see, because there are other questions. So what is the purpose of the mutex in this example? Headshot spy. I'll get to it. Let me see the other questions first. So that there aren't more threads using variable honey. Yes, there are. You have 10 bears and 10 bees. 10 bears eating, 10 bees producing, and 1 farmer. To synchronize, okay, William, indeed, the mutex is meant to synchronize access to honey. Philalita, so the difference between threads and processes is the system is the one choosing one to run. Nope. No, sorry if you get that idea. Both processes and threads are actually scheduled by the system. So when the system kicks in, it doesn't just look at all the threads, but also the processes. However, each process has a default thread, the main one. So you could think that it just looks at all the threads. Right? So processes don't really indicate themselves. Operating system chooses who gets the CPU next. Thread, process, doesn't matter. Okay, Stefan says control the chaos in a way. Yeah, you control it, but only in little pieces. You rely on the chaos. You rely on the operating system to run these things in its best way possible. And you only intervene and bring order where it matters, meaning in the critical sections. The rest of it, you let it be. Okay. I don't think the honey can get to a negative value, William, because when I check if the honey is greater than 0, I have the mutex. And I only go negative if I only eat if it's above 0. So no, honey will not go negative in this implementation. Right, thank you, Berzent, you actually answered it. But if we didn't check yes, it would go negative, absolutely. If we stop the bears from eating until the farmer wakes up, it would never get negative. That's true. Okay, now you'll see there is another mechanism that would maybe let you stop all the bears from eating. But you can probably do that with another conditional variable. So you signal the farmer, and then the farmer will broadcast to the bears, right? Wake them all up when there is honey. This would be a nice example to implement, to see how this can go without relying on the bees to solve the problem in the meanwhile. Because that's what you guys keep suggesting. Well, we don't really care about the bees. If there is no more honey, let the farmer fix it. In which case, the bears have to stop and the farmer has to go fix the problem. But the bees are still there, you see, they're right here, plusing the honey, 10 of them, so they will have an effect too. All right, so with this, I think we're ready to move on to the next example, which is a barrier. So the barrier is a mechanism that waits for a number of threads to reach the same location, and then they all move on. So the functions that you see here, this is just waiting. No, this is just measuring how time it passed since the program started. So this is just for feedback purposes. This one is waiting for a number of seconds, again, just to make the example more readable. And this is the actual meat of the example. So we have a barrier created, initialized, and destroyed. And then we have 10 threads running function f using the barrier. So let me clarify what the barrier is. Sometimes you have a bunch of threads and you need to do something like this. This thread cannot go beyond this point unless those threads reach the same point too, or maybe different points. Okay? If you want, let me think of an example from real life. You know, the actors on the stage cannot start performing until the audience is in the room. So you have a bunch of threads waiting for another bunch of threads to reach a certain point. Okay, so this would be a barrier. So the way we use the barrier, maybe the example with the stage wasn't the greatest. Yeah. We initialize the barrier with a number. This is the number of threads that have to reach the point. And then in the function, we'll just have each function wait a different amount of seconds, like the first one nothing, the second half a second, the third one 1 second. And then they reach the barrier after a certain amount of time. And then they wait at the barrier. And when all of them reach the barrier, they all move on. Let me just execute this, and then you'll get it, how it works. So you see the threads reaching the barrier half a second apart, and when they all reach the barrier, they all move further on. Okay, this is what the barrier is meant for. But the barrier has no idea about who are the threads that have to reach it. All the barrier knows is that it has 10 threads to reach it. And then when 10 threads call wait, all can move on. Otherwise, if it's only 9, they wait. If you initialize the barrier with a larger number than the threads, then they will all be stuck there. Now, an example where this is needed, you may remember this from a previous lecture. I think it was when we introduced pipes. It was the adding numbers in parallel, if you remember. So there were a number of numbers, let's say 8 numbers, and then you had 4 processes or threads in this case, adding one of them adding this number to this one, another one adding this to this, another one adding this to this, and another one adding this to this. So initially you have 4 threads doing simultaneously additions and ending up with this value written here. Okay, now the next round of additions cannot start until all these threads finished the first addition. So this is where you would use a barrier initialized with 4, and after they do the addition, they call wait on the barrier. When all of them called wait, it means all of them did the addition, and then you can move to the second phase, where you only have 2 threads adding numbers as such. So here you would use a barrier of 2, and when both of them reach the barrier, it means that the results are done, and you move to the third phase when only one thread does this addition. So this is one example where you would use barriers. So let's see if there are questions about the barriers. Are we good? It sounds like we're good, but I'll give it a few more seconds. and then go to the last synchronization mechanism for today, which will be the semaphore. All right, so let's move to the semaphore. Okay, this is a good question, Kata. Can we add to an already initialized barrier? No, not really. In this implementation, if you need to, you cannot change the barrier. So in this case, you would actually have to have two barriers already created, one with 4 and one with 2, and you'd use the appropriate barrier. Okay, you cannot change a barrier, and you cannot really reinitialize it. So you just need to have several. So the barrier is a way to avoid race conditions. This is very generic, Irelia. It's basically, I mean, race conditions are so varied. It's a way of synchronizing threads executions. That's the best I can say. Now, will you protect a race? Will you protect a critical region with a barrier? Yes, it is some kind of critical region. Practically, the critical region would be everything that follows the barrier. And you cannot get into there unless everybody has reached that. So yes, in a way, you can say that you can use a barrier against race conditions. Okay, we have William saying, but in this case, after all the threads get to the barrier, for the next step, we only need half amount of threads. So how do we know which threads to stop? I don't know. It's your choice as a developer. Maybe after this thread, you check the thread's index, and if it's odd, you stop it, and you only keep the even index threads, right? There is actually a formula that you can do here, some powers of 2. It's just a little arithmetic to actually choose which threads to let continue and which threads to keep to stop. As a side, these barriers you will find in GPU programming, where you actually need to wait for all the little processors to finish calculations. They're very common there. Okay, let's wait a few more seconds. Maybe there will be more questions. In the meanwhile, I will open the semaphore. Or you can join them in the main thread, and that's basically a very Berzent. I would not call join a barrier, but yes, it is a place where you wait for all threads to get to the same point, meaning to the end. A barrier synchronizes the threads somewhere in the middle of their execution. Join actually just waits for them to finish, which in a way you could call a barrier. But the threads will not be able to continue after that, whereas with the proper barrier, they will just move to the second phase of their execution. You could implement this with joins. Create 4 threads, wait for them to finish, create 2 more threads, wait for them to finish. You could do that as well, joining. Or you can just have 4 threads and reuse some of them. Technically correct is the all right, good. Okay, guys, let's move on to semaphores. Now, semaphores are the last synchronization mechanism that we will talk about. And the way they work is they allow you to reduce concurrency, to reduce the crowd that can get into the critical section. While with a mutex you can say only one can enter the critical section, with a semaphore